Okay, it's equipment review time here. I've got this new GW Instek SFG-2004. It's a synthesized function generator. Basically, it's a signal generator with a DDS chipset. Picked this up from the Farnell trade counter. It was very, very cheap. It's a pretty lightweight unit. See, it's pretty small. Not much to it. Nice tilting stand, works fairly well, and folds out of the way unobtrusively, should you want to put it down on the bench. And it's got the TTL output, the logic level output, and a standard 50 ohm terminated output. Power button, keypad entry, little jog dial. Rear of the unit, we've got the power line entry and a mains voltage switch. This unit does not have USB or RS-232 programmability, and it's not an arbitrary waveform generator, it's just a standard fixed function waveform generator. So I'm not Dave Jones, so I'm going to turn it on before I take it apart, just to make sure it works. Shows the frequency pretty easily, pretty quickly on display. It's powered up and ready. It doesn't actually appear to have an output control switch, so there's a relay that turns on and off, but you can't actually turn the output on or off. Immediately what we see on here is the frequency. You can see it's in kilohertz. The one thing I don't like about this display, and it probably won't come up very well in the video, is it's really quite dim compared to other displays I've seen. It is really dark. The camera's going to overexpose it, of course, and there's a slight flicker on the camera that I can see in the viewfinder, but that's not actually on the display there. So we can enter a frequency in using the keypad, or we can use the jog dial. Now, a little word of caution here, the jog dial is really slow. Look at that. I mean, come on, guys. At least it doesn't skip pulses, but it's really slow, and it misses things. So, I mean, if you turn it a lot, it won't catch up. It just stops. Entering a frequency in is pretty quick, comparably. Say 123.54 kilohertz, and just like that, it's done, and it changes immediately. It supports square wave output, triangle ramp wave output, and a sine wave output. And the square wave output, you can vary the duty cycle. It doesn't appear that you can change the symmetry of the triangle wave. One thing I do like about it is the CMOS TTL output. You can vary the amplitude, which is quite neat, from 5 volt to 15. It's kind of a shame it doesn't go down to 3 volt, because that would make it more compatible with the inputs of many microcontrollers. I'm sure the impedance of this output is probably quite high, on the order of a couple hundred ohms. So you could probably use the 5 volt and then the clamp diodes inside the microcontroller. But obviously that's not ideal. Okay, I've taken the unit apart, and yeah, there's a few surprises in this thing. First thing that was quite surprising to see was this big transformer here. It has a linear power supply. I sort of expected them to use a switching power supply, as a lot of the modern signal generators are using switching power supplies. But then again, I've taken apart an Agilent unit before, and it had a linear power supply as well, despite being a fairly recent design. So I guess in order to get the low noise figure, they decided a linear power supply with a big fat transformer was the best way to achieve that. It's got a nice real main switch, as you can see there. It's actually the lever for the front button here. And there's two boards in this unit. There's one on the bottom, which is obviously the main PCB, and then we've got a little keypad and LED display, one on the front. There's a cutout option for a fan that's not fitted. Incidentally, well, interestingly actually, there's also a cutout for a USB port and an extra BNC on the back, and neither of those are fitted. The extra BNC is probably some kind of synchronization input, and since this thing doesn't have the correct software on it for those features, that wouldn't work. But I do kind of wonder if I just soldered the USB port to that, if this would act as a PC programmable signal generator. Not going to have arbitrary waveform capability because it doesn't have that design of controller, but it might allow you to control the frequency and various other settings from a computer. So I may try that. I'll dig through my stash of USB connectors and just put one on and see what happens. The design is quite surprising actually, because as GW Instek do market this as an FPGA controlled instrument, well, there is an FPGA in it. So yeah, I was quite surprised by the design of this instrument when I actually figured it out. There is an FPGA in here. It's an Altera ASEX. It's a very basic FPGA. It's in a large quad flat package with maybe about 144 leads or thereabouts. And then we've got a little 8-bit microcontroller, an ST Microelectronics UPD3212C. And that's a very basic little 8-bit microcontroller with an 8032 core, which does seem to be quite a popular core with Chinese manufacturers. 8032 and 8052 cores are very popular. I'm not quite sure why. And then the surprise here was, given it's got an FPGA and they're saying it's an FPGA controlled instrument, there's one of these analog devices DDS chips, the DDS on chip solution. So what on earth is the FPGA doing? Well, it's connected to this ribbon here for the front panel display, and all of the signals, almost all the signals appear to be connected to it. So this thing does definitely handle the display, and it appears to handle the button input and maybe the rotary encoder. But then what's the microcontroller doing? It's a rather strange design. Why have they got the FPGA in here? I mean, the microcontroller in this, maybe it's not capable of running the display, but easily a slightly bigger microcontroller would be more than capable of running the display and scanning the buttons. And then if you just got one of these DDS chips, all you do is you just program it over SPI. So the use of an FPGA is just bizarre when they could implement this on just one processor. I mean, yes, the DDS control signals, the data, clock, latch, and so on, do come from the FPGA, but I probed it with a scope. They only get sent whenever the settings change. So I'm guessing the FPGA just either it calculates the values, or the microcontroller calculates the values, passes it over some kind of data link between these two processors, and then the DDS chip updates the output. I mean, FPGA doesn't even control these little relays here, which select the various attenuation and waveform options. So it's all very, very strange. I'm not at all sure why they've done this. The other thing you notice about this board is how little of it is actually soldered. I mean, so much of it is omitted and optional. They've got a huge section of components here that just aren't placed. There's a huge DIP40 package here, and a load of SOIC 14s and a fairly large SOIC chip there, and then all of this stuff down here. Now, I've looked at other models in this series, and it seems the SFG-2004 something, they make the 4, 7, and 10 and 20 megahertz versions of this. Those have a modulation input and a frequency counter input, so I suspect these components are used for that functionality, and maybe when the instrument has a frequency counter, this FPGA is a lot more useful, because that could be used as a high-speed counting device. But that must be quite expensive to implement the low-end models with this kind of design. Why they didn't design it in some way to make the FPGA optional and just run it on a single microcontroller. And the large PCB as well, and the large case for this device. Yeah, there's a few things that I'm a little concerned about. See these capacitors here, they're glued down. But the TO220s next to them are not glued down. And they're just, as Dave Jones would say, they're flapping in the breeze. But they're not, they're pretty well soldered in, but still they're not, it's not ideal. I'd prefer if they could bolt them to the PCB. The mains connector here is a little worrying because it's soldered to the board. The electrical connections are soldered, but actually if you put the cord in it wobbles a bit. It is bolted as well, but I would worry that if the cable were frequently removed and inserted, the solder connections would break. I much prefer the mains inlets that are mounted and then the cable just connects to the board. We've also got the voltage selector input there. Don't set the wrong setting, it'll probably pop the fuses or maybe blow something up more seriously. These things on the heatsink, by the way, I thought they were voltage regulators, but they're actually transistors. And you may not be able to see it very clearly here, but there's a little LM741 op amp next to each transistor, and that appears to be being used to regulate a voltage rail. Why they didn't just go for something like a 7815 is unknown to me. Maybe a cost-saving exercise, but they certainly didn't try and save money in other areas. So it's rather odd, I suppose you could say. Maybe they needed a certain voltage that they couldn't get from an LM78 regulator, but then why didn't they use an LM317 or 337? I don't know. There's also another one of these regulators with a big power resistor next to it, and this is a negative 5 volt regulator, and I'm presuming the power resistor is used to remove some of the take some of the power dissipation out of the IC. It's just widened series of the input, but again, it's kind of flapping in the breeze. It's also, I mean, why is it over here? All the power supply stuff is in this area. You've got a fairly sensitive DDS chip, you know, with an internal voltage reference that's going to be temperature sensitive. Why wouldn't you put the negative rail regulator over by the components that get hot, and then just use a power plane to connect it? Well, I suppose maybe the reason they haven't done that is because it's a 2-layer board. There is no there's no internal ground or power planes. Output stage, it's pretty common actually. They're using discrete transistors to drive the output, and a few other components, a few op amps and other transistors to bias these devices. It's got a standard 50 ohm output. They're just using these surface mount resistors here. I'm not certain if it has current limiting, but it does have some resistors in series with the output of the transistors, so if it's not got some kind of foldback current limiting, it probably just has a hope the transistors don't overheat style current limiting. It's got one high-speed relay here. I suspect that might be the 20 dB attenuation relay, and then it's got a standard relay there. There's another 2 standard relays across the board. I guess one other comment I can make about this design is how all over the shop it is, really, in terms of layout. I mean, I know I mentioned the voltage regulator here for the negative 5 volt rail is over here when the power supply stuff is on the other side of the board. But also, I mean, if the DDS chip is here and the output's here, well, why? It's very far from where it really ought to be, because we've got this relay here which appears to select between the square wave and the sine triangle output, because this is one of those analog devices chips that outputs either a sine or a triangle wave. They then compared the sine wave with a voltage reference, and that generates a pulse width that they use for the duty cycle. Strangely, they don't actually compare the triangle wave. I have checked this. It produces a sine wave when it's in the square wave mode, the path that's not connected. So that's rather strange. I'm not sure why they've done that. But it might explain why it's only got a 20 to 80% duty cycle range, rather than the more common 5 to 95%, at least at lower frequencies. It's 20 to 80% regardless of what the frequency is set to. But yes, it is strange that they put the DDS chip over here, near the FPGA and the digital stuff, but then the output stage over here. Why? I mean, you've got plenty of space here. You could have put the DDS chip over here. I guess the only reason they may have done that is because they've got the sweep function input, and they need the DDS chip near there. I'm guessing they modulate the clock of this DDS chip to enable the sweep function. And in order to do that, they need to be near the clock. But still, the clock for that is over here. So, I mean, it's just rather strange. So, why are they doing... Who laid this out? So one of the other things I noticed when I was taking this thing apart is this little potentiometer here. And since it's near the FPGA and the microcontroller, I thought, could they be using this potentiometer to configure different options? Unfortunately, that's not the case. I have seen it done before in a design where the voltage on a pin, when the processor booted up, defined which model it was. That was actually using external surface mount resistors, and they would configure it to one of various options depending on what resistors were placed, but this just sets the amplitude of the square wave. Which raises another question of why the hell is the amplitude for the square wave setting all the way over here between two processors when the comparator that generates the square wave is actually this device here? Why? What? Who the hell laid this board out? Was it the intern? So I've got a trusty Rigol DS1074Z here. This is the modified 100 meg bandwidth model, and we've just connected the output without a 50 ohm terminator to the scope, just showing on channel 1 right now. So we're at 121.54 hertz, which is a rather strange frequency. Let's just try 100 kilohertz. You see this oscilloscope agrees 100 kilohertz. So that's nice to have. The duty cycle is 55%, so you can see the on period is slightly more than the off period. So we can set the duty to 50%, and the waveform changes immediately, which is nice. We can then change the duty cycle, let's say, to 20%. Changes immediately. Changing waveform. Appears to click an internal relay. So one thing we can note about the square wave is actually a fair bit of ringing on the edges. So if I just zoom in there, now obviously I'm not terminating this properly, so some of this ringing might be as a result of that. But that ring period there, it might be a cause of some concern. If it is, I will try and get a properly terminated, a proper terminator, and then retest it. There's some jitter on the output. I mean, some of this might be down to the oscilloscope. Obviously, it's only the base end, 1074Z. Jitter, I can't really give you an accurate measurement of that, but it looks like it's jittering about plus minus 5, maybe 10 nanoseconds occasionally. For 4 megahertz signal generator, that sounds pretty reasonable, really. This ringing is going to be fairly consistent with frequency, but one thing I have noticed is it's not that consistent with offset. So if I move this offset, change it, we get this kind of ramping here, and the ringing is reduced. If I put the offset back up, the other side kind of does that. There seems to be some kind of clipping. So as long as you keep the offset within a fair range for the square wave output at least, it doesn't seem to clip it too badly. Obviously you can just put it in the cow position. 4 megahertz sine wave, the highest frequency the instrument supports. A bit of jitter on the output. Then again, not expecting too much, but the sine wave is very clean. I was expecting to see some DDS harmonics, but I can't really see them. I could put the math and FFT function on. Yeah, we've got the first harmonic here, and we appear to have a second harmonic component down here. So it's not doing too badly, at least. If 10 dBV, yeah, 10 dBV, we're not doing too badly to have something at least 40 or 50 dB below this first harmonic. Again, this is a fairly low-end instrument, so I'm not really expecting too much from it. We can actually see what appear to be the DDS clock frequency spurs, because this thing is probably clocking the DDS at something like maybe 20 megahertz. You're going to get an offset frequency and a multiple of this output frequency, and they will be reflected in the output, and the output filter essentially will try and remove as much of this spur noise as possible whilst preserving the first harmonic, which is what you're really interested in. Obviously the output filter gets more difficult when you're dealing with something like a triangle wave. So the frequency at which you can use a triangle wave is different to the frequency at which you can use the sine wave. The triangle wave is limited to 1 megahertz, as you see there. When I switched to from sine wave to triangle wave, it gave me an error message. 1 megahertz is still pretty decent for a function generator to have a triangle function, and we can see on the oscilloscope the FFT, so we're getting every odd harmonic essentially there. And yeah, I mean, again, the triangle wave output is pretty clear. There is some distortion as we're hitting the frequency limit of the output. So yeah, we started to see some of the filtering of the DDS, and if you're at non-DDS multiple, you will be able to see this kind of rippling here. If I vary the frequency, it may be more prominent, and that's basically, see, the rippling has gone away now. That's basically because you've got a DDS clock and the output frequency, and they're not in perfect, they're not perfect multiples of each other, and so they kind of have a beat frequency between them. So if I vary that, you can see now it's fairly strong. Just zoom in there, you can see a quite strong beat frequency, and that's at 984 kilohertz. Theoretically, if I could measure that beat frequency there, I could actually determine the clock frequency of the DDS, or at least a multiple of the clock frequency. I would suspect the clock frequency is somewhere in the 20 meg or so range, because that's probably sufficient for the sine wave and give enough samples to the triangle wave to get a megahertz output. This would be quite useful for anyone who's doing circuits involving pulse width modulation, because when you've got a triangle oscillator, you've got very good reference. You don't have to build your own oscillator. Of course, you can vary the frequency, you can vary the amplitude very easily, vary the offset, and if you have set your circuit up correctly, then your offset could actually function as your pulse width modulation input, and you just kind of set your comparator to trigger it to say 5 volts. Obviously you get some kind of distortion there as the amplifier and the output clips. But as long as you stay within a reasonable range, the amplifier doesn't clip, and so everyone's happy. The scope's losing trigger there as well. Yeah, yeah, I'm pretty impressed by the signal performance, as you probably tell. I didn't spend much on this. I think maybe some of these little niggles I'm picking up on, maybe for a £240 instrument, they'd be disappointing, but given I paid about £80 for it, they're not really disappointing, if we're going to put it in that kind of way. Other functionality on the unit, we have store function. Never used it, have no need to use it myself, but could be useful if you do, let's say, factory work. You might want to store one of several presets, and you can quickly switch to them. Myself, I would probably change so often, and given it's so easy to just enter something in, and it doesn't have many settings, it wouldn't exactly take much time. You got a simple minus 20 dB function. Just press the shift button, and the output is attenuated by 20 dB, and that does also click a relay across. The TTL function, that appears to click a relay on and off, so it does have an option to turn the TTL output on and off, but it doesn't have an option to turn the main output on and off. And this is actually sort of a problem in a minor way, but it's definitely something worth paying attention to, and I'll just demonstrate why. So I'm going to set this thing to 10 kilohertz, and one thing you might do is use this as a pulse width modulation reference, as I mentioned previously. And it is not impossible that you might at one point just go and power. I've set the oscilloscope to roll, and you might just turn your signal generator off. And you can probably kind of tell where I'm going with this. But yeah, it basically saturates its amplifier. For some reason, I don't know why, when some of the rails collapse inside the unit, you can see it starting to clip there. It's probably the negative rail collapsing, and then the chip resets and it goes high. Most units I've encountered, the high-end units, like the Agilent units, actually monitor the AC waveform, and as soon as the AC goes away, they click the output relay off, so the output just dies. Perfect. This one doesn't. This is actually quite tame, but what it does, it turns off and then it goes up again. On some waveforms, especially if the offset's quite high or particularly low, it will pulse several times, or it will drop frequency somewhat arbitrarily. So it's definitely something to watch out for if you have this connected to a setup, and you might just power it off without thinking. You might just turn the unit off. Don't think about it. But this could perhaps cause your transistors in your motor controller to switch on at the wrong time, and bang, go a set of transistors. I just wanted to add this other odd thing I've noticed about this instrument, and that's this minus 20 dB option here. Fair enough, it's pretty common. And this minus 20 dB option here, which is a pull-out switch. So it has a software-controlled minus 20 dB and a hardware-controlled minus 20 dB. And if you save the settings, it saves the software control setting, but it doesn't save the hardware control setting, of course, because this is a physical switch. So why do they have a minus 20 dB option there and a minus 20 dB option there? Well, the answer is if you enable both, you get minus 40 dB attenuation, which seems fair. But then why wouldn't they just give you an option here to enable an additional relay for, say, a minus 40 dB option, or give you various attenuation settings from here? So why do they give you an additional setting that's a switch and then one that's a software control? It's just strange. Another thing I noticed, and this actually seems more like a hardware bug. So I've got the oscilloscope here connected to the TTL CMOS output, and I set the duty cycle to 20%, so this seems quite reasonable. It's 20% duty cycle. Waveform. All reasonable, right? I'm just going to pull this TTL CMOS adjust. Just pull it out, which should switch it to the TTL option. And it sets it to 5 volt. And it inverts the phase. Oh wait, push it in to the TTL. Which is a fixed amplitude. If I turn the dial, it doesn't do anything. I pull it out, that's CMOS, and you can vary the amplitude. But the CMOS, it has the opposite polarity. It's not actually inverting the waveform, it's just inverting the logic level. It's all rather strange. Incidentally, it does actually go down to 4 volts on this scale for the CMOS, but doesn't go down to 3, which I think is a shame. So yeah, something to keep an eye on there if you do use this output. On a lot of instruments I've encountered, usually the TTL output doesn't even vary duty cycle with the square wave. It should just be related to the zero crossing of any waveform. If you change the wave to a non-TTL wave and then switch the TTL on, so that's triangle wave, you get 50% duty cycle. But something else you might have noticed, if I change the wave to, say, let's turn the TTL off, the output goes high. So the TTL output is off right now, but the output is stuck high. And yeah, you can't vary the amplitude of that. If you pull the CMOS out, then yeah, that sticks to 0. You put the TTL in, and the output's stuck high. So, what are my thoughts overall on this unit? Well, I quite like it, and I didn't pay too much for it. And I've put it on my bench now, above my GW Instek power supply and my Tagasaki power supply there. So I'm quite pleased with it, especially given the price I paid for it. But there are quite a few niggles I have with the unit that may mean it gets replaced in the near future if I find something that has better performance than this GW Instek unit. It's a good my first signal generator, I suppose you could say, in that way. But as a professional instrument, it's got a few too many maybe little niggles and oddities that mean I can't really give it a solid recommendation in that area. But if you've never used a signal generator before, and you just need something that will function as a basic function generator, then this is perfect. and especially if you can get one pretty cheaply, then go for it.